Okay, imagine you're trying to point a super powerful telescope at a tiny, distant star. Simple enough, right? Now imagine you're doing it from the top of a giant, wobbly pogo stick. That's pretty much the challenge engineers face with modern satellites. And the solution they found, well, it's this brilliant mix of old-school math and cutting-edge AI, all thanks to a very clever kind of treasure map. Let's dive in and see how they pulled it off. You see, satellites aren't these perfect, rigid blocks we imagine. They've got these huge, kind of flimsy solar panels and antennas that bend and vibrate every single time the satellite tries to move. So the billion-dollar question is, how in the world do you get a wobbly, flexible machine to aim with rock-solid, perfect precision? So here's our game plan for this explainer. We're going to break down how a team of researchers cracked this exact problem. We'll start with why these satellites are so hard to control, then get into the big dilemma engineers face. After that, we'll uncover the treasure map shortcut, meet the AI search party they used, see how it all held up in a real test, and finally look at what this could mean for, well, pretty much everything. All right, first things first, let's really dig into the heart of the problem here. And honestly, this isn't just about satellites. It's about the challenge of controlling any complex system out here in our messy, unpredictable real world. You know, the fundamental truth of engineering is that our computer models are always just a little too perfect. On a screen, we can design a satellite as this flawless, rigid box. But the second you actually build it and launch it, it becomes this complex, living thing that vibrates and flexes. And that's where controlling it gets really, really hard. So this gap, this huge gap between the perfect computer model and the messy reality, it creates a massive dilemma for engineers. The problem is, their best, most powerful tools are designed to work only in that perfect imaginary world. It really comes down to this. On one side, you've got linear systems. Just think of these as our simple, ideal computer models, where everything is predictable and follows neat, straight lines. But on the other side, you've got nonlinear systems. And that's the real world. It's complicated, unpredictable, and just full of weird feedback loops and vibrations that make control a total nightmare. Now, for that simple linear world, engineers have this absolute powerhouse of a tool called the Linear-Quadratic Regulator, or LQR. I mean, it's the gold standard. It can calculate the absolute mathematically perfect way to control that ideal system. It's a beautiful, elegant solution, but it only works for the perfect model, not the real thing. And that lands us right at the central dilemma, doesn't it? We have this perfect key, the LQR, but it only fits a lock that exists inside a computer. So how can we possibly use it to solve the control problem of a complex, messy, wobbly satellite out in space? Well, the answer comes from this brilliant aha moment. Instead of throwing that perfect key away, the researchers realized they could use it to draw a treasure map. This is where it gets really clever. Here's the big idea. Trying to find the perfect controller settings for the real satellite is like searching for a tiny piece of treasure in a massive open field. It's just computationally impossible. So instead of using the simple model's LQR solution as the answer, they used it as a guide, a treasure map that tells them exactly where they need to start digging. So, how do they draw this map? Well, at any single moment, the LQR solution doesn't give just one perfect answer. It actually gives a whole range of pretty good possibilities. And this range of solutions forms a shape that kind of looks like an hourglass. It's a promising area, for sure, but it's still way too big to search through. But here's the genius part. You don't just look at one hourglass. You calculate one for the next moment in time, and the next one, and the next one after that, and you layer them all right on top of each other. The idea is that the true, perfect solution has to exist in the spot where all of these hourglasses overlap. And there it is. That's the final step. The intersection of all of those different hourglasses creates one tiny, super focused target area. That massive, impossible search field shrinks down to a single, manageable spot. That's the X on our treasure map. That's where the treasure is buried. Okay, so we've got our map, and we've got our X that marks the spot. Now, all we need to do is send in a high-tech search party to do the final bit of digging. And for that, we turn to some amazing algorithms that are inspired by nature itself. The researchers use two main types of evolutionary algorithms. First up is a genetic algorithm.
This basically mimics natural selection, survival of the fittest, but for computer code. It tests a bunch of solutions in our target area, breeds the best ones together to create a new and better generation, and just keeps repeating that until it finds the best one. The other is particle swarm optimization, which is kind of like a flock of birds all looking for food. Each particle searches the area, and they all talk to each other, sharing info about where the best spots are until they all swarm to the single best solution.
So, to put it all together, the whole process is this elegant four-step dance. First, you model both the real, messy system and the simple, perfect one. Second, you find the perfect LQR solution for that simple world. Third, you use that solution to draw your treasure map for the real world. And finally, you unleash your AI search party to find the treasure. Simple as that. Now, this all sounds fantastic in theory, right? But the big question is, does it actually work in practice? Well, the team didn't just stop with computer simulations. They put their method to a real-world test. And this is it. This is the experimental setup they used. It's designed to perfectly mimic the dynamics of a real satellite, with all its real-world wobbles and imperfections. This isn't a simulation anymore. This is where the rubber really meets the road. And here is the proof. Seriously, this graph is the money shot. The black line, that represents the theoretical, mathematically perfect performance from the LQR model. That's the ideal goal you could only dream of hitting. And the colored line, that's the actual performance of the real system using this new method. Just look at how closely it tracks the black line. It's an almost perfect match between the messy real world and the ideal theory. It's incredible. The numbers back this up big time. The LQR's ideal performance score, which they call J, was 0.425. The genetic algorithm, in the real world, got a score of 0.426. The particle swarm got 0.428. I mean, those numbers are practically identical. It proves that the treasure map led the AI search party to almost the exact perfect spot. So why does all this matter? Well, this breakthrough is about so much more than just keeping satellites steady. What we're looking at here is a whole new blueprint for how to control all kinds of complex systems. I mean, think about it for a second. This same treasure map approach could be used for pretty much anything that's too complex to control with old-school methods. We're talking about ultra-precise robotic arms for surgery, complex machines in factories, or maybe even stabilizing entire electric power grids. The potential applications are just enormous. If you take just one thing away from all this, let it be this idea. The incredible power of using a solution from a simple, ideal world to create a treasure map that lets us navigate our complex, real one. It's really a fundamentally new way of thinking about these huge, hard problems. And that leaves us with a really fascinating question to think about, right? From economics to biology, what other seemingly impossible problems could we finally crack if we just stopped trying to solve them head-on and instead first looked for a map in a simpler, more ideal world?